Welcome to session 22. In today's session, we're going to review the long and short base operation of the p-n junction. We're going to summarize a little bit about the diffusion and drift currents. We didn't know we had drift currents in a p-n junction, but we're going to see that we really do, and we're going to introduce that concept. And then we're going to look at our first two junction devices. And that will be something called the ISO junction and the pin diode. And we're going to analyze specifically the pin diode in some detail, and hopefully that will be a good introduction to our next big topic, which is the p-n junction transistor. But to get us started, let's listen to some Mozart from Mozart's Don Giovanni, La ci darem la mano, and we'll see you in about 3.5 minutes.
Ci sposeremo, la ci darem la mano, la mi dirai di sì. Vedi non è lontano, partiam ben mio da qui.
Andiam mio bene, a ristorarne bene, ogni notte andiam mio bene, a ristorarne bene,
Okay, so these are some of the topics we'll be covering today. We'll be reviewing the general case that we did in our last session. We'll be looking at long and short base operations. By long and short base, I mean long where the quasi-neutral region is long, and that's not so good. fact, it's very bad. And short is where the quasi-neutral region is short, and that also implies that recombination can be neglected in the short base, and generally in the long base recombination cannot be neglected. We'll be summarizing diffusion and drift current components in a p-n junction, and we'll be pointing out that wherever we have diffusion, we're generally going to have drift. They are not mutually exclusive. In fact, many times they go together. And we saw a case, for example, in equilibrium, where the diffusion and the drift currents were precisely equal and they were opposite. And that's what gave us a net zero current. And of course, net zero current is what we mean by equilibrium. It's almost another definition. But generally, we'll see wherever we have diffusion currents, drift currents are not far behind. And then we'll be summarizing specifically diffusion currents for excess hole carriers in n-side silicon. Of course, we could do it for excess electrons in p-side. Same thing. We just chose generally to work with a p-n junction with p on the left and holes going into the n-side silicon. And then we'll be, I'm going to present what I call a conundrum. Have a look at what a conundrum is. It's a sort of like a paradox, an issue which we really need to talk about. And I'm going to define it and then give you my take on it. And then finally, we'll be looking at our first two junction structures, two junctions, and three separate components. We'll be looking at the iso junction, which is not terribly practical. I don't know of any practical applications for the iso junction. But then we'll be looking at the pin diode, two junctions. There's a junction between the P and the I, and there's a junction between the I and the N, and there's three slabs. 1, 2, 3. P silicon, intrinsic silicon, and N silicon. Okay, so if we look at these two extreme cases, the good case, and in fact I even repeated it because it's I want to emphasize, this is the good guy. This is where the excess carrier concentration varies linearly with position. This W is the end of the quasi-neutral region, so the contact is right here. Sometimes I call it X sub C, sometimes I call it W. You'll hopefully forgive my sloppiness. The point is, we have a linear variation, and because we have a linear variation, we have a constant diffusion current. The not-so-good case, and that's understatement of the year, this is really a lousy case, because what we have is a reasonably high variation of excess carrier concentration at the point where the depletion region contacts the quasi-neutral. This is where x equals 0. So here we have a nice, healthy excess carrier concentration, but it decreases. It decreases exponentially. So before it gets to the contact is somewhere in this region here, the excess carrier concentration dies out, which means that the current goes to 0. And that is actually really, really bad, because that's a useless device. So if we look at the diffusion current, it is proportional to the gradient, or the first derivative, of the excess carrier concentration. I should have perhaps put an N here, a sub N, but we get the idea. For example, here I have the sub N. So, and let's look at the units here. The units on the left side for current, this is whole current, are, well, it's current, which is coulombs per second, but it really isn't current. I shouldn't have said current. I should have said current density. It's current in amperes per square centimeter, and the area here is the cross-sectional area. So the units on the left side are coulombs per second per square centimeter. The units on the right side, well, the denominator is numbers per cubic centimeter, so the units are centimeters to the minus 3. The denominator is just centimeters, so the total units on the right side are centimeters to the -4th. Therefore, the units of A, I just take this over and put it on the left side. Centimeters to the -4th become centimeters to the +4, which cancels out the centimeters squared, at least two of them. So the units of A must be coulombs per second with centimeters squared on top, not on the bottom. And we know that A is equal to Q times the diffusion constant, Q being in coulombs. So therefore, the diffusion constant units are centimeters squared per second. And that's very useful because knowing the diffusion constant units, I can get the units, for example, of mobility simply by using the Einstein relationship and by noting that the Einstein relationship is d over mu is kt over q, that nice rhyme. So if I know the units of the diffusion constant, I can get the units of the mobility very simply just by using the Einstein relation. Okay, now we found, kind of icky mathematics, but we found that the general expression, not making any assumptions whatsoever for the excess carrier concentration as a function of position, this is holes again in the n-type material, is equal to the excess carrier concentration, not at equilibrium. There's no zero here. At the 0 point, at the demarcation between the depletion region and the quasi-neutral region, that's the 0 here. And I can substitute in for this guy, saying this is the equilibrium. That's why the 0 is here, and multiplied by the boost. And this number can be quite large indeed. This will be small. This will be like, well, not that small, maybe 10 to the 3rd, 10 to the 4th. This can be 10 to the 11th or even greater. And to find the current, I just differentiate the excess carrier concentration with respect to x. And this is the only term which has an x variation. The derivative of the sinh is equal to the cosh. And that's why I have the cosh here. And here it is in all its glory. This is the current density of holes in the n-type region. I have an expression exactly the same thing for the electrons in the hole region, except some of these constants would be different. dP would turn into dN, LP would turn into LN, and ND would turn into N sub A. And other than that, everything would be pretty much the same. So here's something a little bit new here, that from the general expression sitting here for excess carrier concentration, I can find my two special cases, the good and the bad. This one here is the not so good, not so bad. It can be either way. It can go either to the good side or to the bad side. So the good side would be when the diffusion length is much greater than the quasi-neutral region, and in that case, the sinh for very small values of the argument reduces to a linear function, because the sinh of x for x small is proportional, is approximately equal to x, just like the sine. The sine, if I measure the argument of the sine in radians, the sine of the angle is approximately equal to the angle. And then I get a constant, what? A constant diffusion current. That's the good one. Now, the not so good one is the opposite. Here it's less than, and here it's much greater than, and then I get an exponential, and that's the one which is not so good. And of course this term will basically go away because it's 1 over 1, and I get an exponential term that is this guy right here. That is not good at all. Okay, so again we said the total diffusion current is the P-type over here, which we, where is it? Right here, 1276. That's this one right here, plus the excess electrons, or the electron diffusion current on the P side. Okay, so in this section I'd like to summarize, not mathematically, but more kind of using cartoons and pictures, all of the different charge motions. And let's take a look at them one by one. Let's see if I can get this all in the same picture. Oh, okay, good. So one is minority holes. Minority holes moving to the right in N silicon. Minority holes, where are they? Minority holes moving to the right in N silicon. That's the one we've been dealing with pretty much exclusively. The holes start here and they move into silicon and they become minority carriers, and they can either move through without recombination, the good case, or they can recombine and die out, the bad case. So that's first one, minority carriers moving to the right in silicon. That is a positive current. Majority electrons moving to the left in N silicon. Now, electrons in the N silicon will move to the left. Why is that? Because I have a positive terminal here and a negative terminal here, and the positive terminal will attract electrons in the N silicon moving to the left. That's a positive current. But how do they move? Well, these guys move through diffusion, but these guys, they're not diffusing. They are majority carriers. They don't move by diffusion. They move by drift. So we have one component which is diffusion, and we have electrons which are moving by drift. We have exactly the same thing on the other side. We have electrons which move by diffusion. Where did these electrons come from? They came from here. The electrons which were majority carriers, which are moving by drift, move into the P-side silicon, and there they become minority carriers, and they move by diffusion. Holes on the P side, they're the ones that become minority carriers, move by drift, and they move from the P side into the N side, where they become minority carriers. So we have drift turning into diffusion. We have drift turning into diffusion. And that is illustrated here by just basically what we've been talking about. So we'll repeat it. And the conditions are summarized below. We have in the P silicon, which is heavily doped, we have a little bit of drift, and I should say a fair amount of drift and a little bit of diffusion. In the lightly doped, we have a lot of diffusion and a little bit of drift. Well, why do we have a little bit of drift in the moderately or lightly doped? The reason is the charges are less. Remember, the drift current is proportional to the number of charges. In fact, it's N, E, V, where V is the velocity. So as N goes down, we have less drift current. And here, however, we have heavily doped. We have lots of charges, so therefore we have lots of drift. But the diffusion is less. So if we add these two guys up, and we add these two guys up, we get the same thing. We get the same current. And this is illustrated here. The point being, as the drift goes up, the diffusion goes down, and it's the same thing here. The drift goes up and the diffusion goes down, such that the overall current, adding these two together, is constant. And here, basically, section, this should be 1221, not 2121. Anyway, this section here, which is from the text, is essentially just a rehash of everything we've been talking about. So you can just read that over, and there's nothing new here. And then we're going to start on what I would like to call, for want of a better word, a conundrum. So let's go back to figure 1228 and look at these different curves here. This is the easiest one. This is the bad case, but it's easy to analyze. It's a simple exponential. And what happens is that the objective holes stream into the N region. This should be N. Let me correct that. N region. They recombine with electrons, and they essentially die out before they reach the right contact. In case 4, the same thing happens, but this is the contact right here. We call it either X sub C or W, it doesn't matter. But somehow, miraculously, the same time they die out, they also reach the contact. Again, not a very useful device, because the diffusion current here is essentially 0. However, at least it's relatively straightforward to analyze. Curve 3 is where they don't die out, and somehow there's leftover excess carriers when they reach the contact, but there's a discontinuity here in the current, because we have a finite and then we have 0. So that means the diffusion current must be infinite, which is kind of silly, but not so much. Let's take a look at number 2, which is the good case. The excess carrier concentration varies linearly, and I'll just read what I wrote here. No recombination takes place. That's why it's linear. That's either because the recombination time is very large, or the neutral regime is very small, or both. If that's true, it must be that all the holes that enter the N silicon diffuse through without being recombined, and they all arrive at the contact. But they're 0 at the contact. That's what it says. The excess hole carrier concentration is 0 at the contact. The only curve where it's not 0 is 3, which is a kind of a crazy curve. So where did they go? On the one hand, they're 0, but on the other hand, they all diffuse through and they all arrive at the contact. So that's the conundrum. And I'm going to propose a solution to that, which may or may not be true, because I've never been able to shrink myself to sufficiently small length to figure out what's going on to observe it. And we can't observe it, so we can only make models. So I'm going to say that the solution is when these excess holes in curve 2 arrive close to, maybe not right at the contact, but they arrive in this region right here, they see a very large electric field. These are holes, and they see a large negative electric field, and they're swept in to the contact and go around the circle. Again, I'll just go back here. Oh my goodness! Oh, here it is. They arrive right here. This has a negative potential. This has a positive potential. Pushes holes. They get to right around this region right here. They see this large external electric field, and they're swept up. And that's why they go to 0. So I'm going to propose that in curve 2, it's diffusion, 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 but all of a sudden it becomes more and more and more drift, and all this area over here, or this region over here, is drift current. Okay, just one more comment before we get started. It could very well be that this good curve here, too, is a combination of drift and diffusion current. Not only here, it could be right from the beginning, because this W for the short base is very small. So it could be that because this point x equals 0 is very close to the contact, that the holes feel a strong electric field even when they're first starting out. So it could be a combination of diffusion and drift for the entire procedure, for the entire journey. And that's why the holes are continuously being sucked out, but also continuously diffusing. Again, I'm not sure. I've just heard the issue raised in a number of relatively advanced lectures, and I never heard a reasonable explanation that I felt comfortable with. So I'm just presenting an alternative possibility here. You can explore these issues of the relationship between diffusion current and drift current. I believe it is in problem 13.3. So I think that's a good problem to review, because it explores these issues in some detail. It's a standard problem, but it's a good solid problem. Okay, so now let's take a look at this thing called the isojunction. And isojunction means iso is same. Another word for same is epi. Epitaxial, same layers. Isojunction means, well, is it a junction or is it not a junction? Well, it is a junction because the dopings are different, and therefore the Fermi levels are different. But it's the same type of doping. At the left hand, we have an N plus, a degenerately doped or highly doped layer, and then in the middle we have a moderately doped or a lightly doped. And I've chosen here for the N plus of 10 to the 18th. That's actually not quite degenerately doped. I think degenerately doped probably would be more like 10 to the 19th, but it's highly doped anyway, even by today's standards. And then for the N and the P, these are both doped to the same magnitude. One is N and one is P, and they are lightly doped at 10 to the 15th. So we're asked to draw the charge density curves, the electric field, and the energy band diagram with as much detail as possible. I'm not quite sure what that means. Just draw it, and that's really what that's all about. And then we're going to calculate the built-in potential. There's actually two potentials, one here, barriers or band bending at this point, and there's another one here. This one is fairly straightforward because it's just 10 to the 15th, 10 to the 15th. This one's a little bit more interesting. Indicate, this is purely qualitatively what would occur to the energy band diagram, the Fermi levels, when light is absorbed, and we have a small forward bias applied to the terminal, terminals being one terminal here and the other terminal there, not in the middle. I don't believe we're able to access the middle layer here. And so we are asked to just qualitatively describe what would happen if you apply a forward bias or a reverse bias. Okay, so the only interesting thing, or the really interesting thing about this is that we have an N plus in the N region. Those are the two new regions. And again, it's called an isojunction because same type of doping, but just different magnitudes. Okay. So the idea here is that the Fermi levels here in the N plus is higher than the Fermi level in the N. So when I bring these two materials together, the Fermi level here must fall and or the Fermi level here must rise so that they become congruent. And what happens is I uncover fixed positive ions in the N plus region as compared to the, and that's shown here, but the charges must be equals. There are no fixed ions in the N region to uncover. All the fixed ions here are going to be uncovered in the N plus region. What we have here, however, are mobile electrons. So the mobile electrons, due to this electric field which goes from left to right in this case, and we know that because the bands bend down in the N region, so that what happens here is that mobile electrons are forced over to the interface. This point right here, this interface is this point right here. That's the point A. Okay, so one more comment before we continue. I should have said this a little bit better here. So we look at point A. Fermi level here is higher. Fermi level here is lower. In order for the Fermi levels to equilibrate, this guy, Fermi level has to come down, which means that we have a depletion region. We have a region at the interface, the metallurgical junction, which is less highly doped. In fact, it goes to intrinsic, uncovering positive ions, donor ions, whereas here the Fermi level goes up, which means at the interface it becomes more doped. So instead of uncovering positive donor ions, it actually attracts electrons. And that's exactly what we see here. Electrons being attracted means negative at the interface, whereas on the N plus side, we uncover positive fixed ions, and there is a positive charge density. At the other interface, B, that's a standard one. We uncover positive ions on the N side, negative ions on the P side. They are equal doping, therefore the charge densities are equal, and that's quite conventional. So if we look at the electric fields, since this is the charge density, the electric field goes from left to right in the positive direction. Here it is linear, slope up, and here it is exponential. And that's what we have at point A. I probably should have marked this. Right here is point A, right in the middle. And at point B, which is the conventional junction, we have, again, positive, because N uncovers positive ions, P uncovers negative ions, so the electric field is from left to right in the positive direction, and the slopes, oh gosh, I'm not sure that's equal. They should be equal. They should be. This should be literally an equilateral, not an equilateral, but not an isosceles triangle with equal slopes. So if you look at the energy barrier, the energy band diagram, the energy barriers on the N side, it's very highly, on the N plus side, very highly doped, and then on the more conventional side, these should be equal dopings. They really don't look that way, and I apologize for that. This should be about as, this should be closer to the valence band, and this should be a little bit further away from the conduction band edge. And if you look at the barriers, that's fairly straightforward. At the N plus N, we just put in the dopings, and we get a very small barrier of less than 0.2 EV. And at the more conventional, or the conventional junction, each side is 0.3, so it's 0.6 for total. At this point, where is it? This point is 0.6. 0.3 here, 0.3 there. We've seen that before. 10 to the 15th is 0.3 EV. Here it's 0.18. So the entire barrier is just the sum of those, or 0.78. So if you shine light on it, light would be presumably absorbed. We have a non-equilibrium situation, quasi-Fermi levels on both the N and P side, but because the N plus side is so heavily doped, it would not be affected at all, and the only effect would be on the lightly doped N and P regions. And the same applies for applying a forward bias. Forward bias, we would contract the depletion region here, although this depletion region would not change hardly at all. And the same thing with reverse bias, we would expand the depletion regions at point B and not hardly affect anything at point A. Okay, so that's the iso junction. Now let's go on to the PIN diode. Just to be a little bit ornery and nasty, I reversed the dopings. Generally, we have P on the left side and N on the N side. I just want to emphasize that PIN doesn't mean that P is always on the left side. It could be NIP. It's the same thing. So the N doping is 10 to the 16th. The P doping is 10 to the 15th. So we have a relatively moderately doped on the N side and a lightly doped on the P side, and then intrinsic with essentially no doping at all, of about 1.5 microns in the middle. So we're asked to find the built-in potential and sketch the field distribution and lanes to the depletion region. I should say the width of the depletion region. And compare the maximum electric field to the PIN diode to the PN junction diode. We would expect that the electric field, because it is spread out, we have this intrinsic layer in the middle, we would expect the electric field would be somewhat smaller, and we're going to show that in some detail. Okay, that explains what's happening in the intrinsic region. So first, a little bit of explanation of what's going on here. We can look at these two interfaces right here and right here as the electrodes of a parallel plate capacitor, and the distance between the electrodes would be the width of the intrinsic region, 1.5 microns. And what we're saying here is if we separate the plates holding the voltage constant, you make more of a separation, then C decreases, and we're going to find that the capacitance does indeed decrease in the PIN diode versus the PN diode, and the charge is going to decrease as well. Okay, so first let's find out the barrier for the whole caboodle, the whole thing. It's just the product of the doping densities. We've seen this a number of times before, 10 to the 16th, 10 to the 15th, and we get 0.66 volts. That is the entire voltage which is dropped between the left terminal and the right terminal. It's now dropped, however, across 3 regions. There's a depletion region here where we get some drop. There's a depletion region here where we get some drop. And there's a region here in the intrinsic where we also get drop. We'll show that most of the drop is across the intrinsic region. Of course, there's no drops across, essentially no drops across the quasi-neutral regions. So if you look at the charge, the heavily doped region is on the N side, and it will have about, actually this is not shown to scale, it will have about 10 times the height of the P side, but the P side will be wider, and the areas of the depletion, these are the depletion regions, the areas of the depletion regions are precisely the same. I know it's the depletion region because it has WN. If it just had W without the N, then I'd be more thinking of quasi-neutral, but with the N, it's a depletion region on the N side. This is the depletion region on the P side, and this is the width of the intrinsic. So this is what I expect the electric field to look like. These are conventional. A highly doped N region produces a large slope. A lightly doped P region produces a smaller slope. In fact, again, not to scale, this should be, if anything, a little bit steeper, and this should be much, much more shallow. It should be more or less go out like that. Why is the field here constant? Because there are no fixed charges. When I have fixed charges, I have an increasing field. Charge always produces field. In this case, positive over here, which means that the field goes from left to right, and it is indeed positive, and the slope is positive. P, the field decreases and goes back down to 0. These are the quasi-neutral regions in the P region, and this is the quasi-neutral region in the N region. If we look at the energy, then we have parabolic in the N region, and it's very small, and we have parabolic in the P region, and it is much wider. And in the intrinsic region, the voltage is linear. That's exactly what happens in a standard sort of run-of-the-mill parallel capacitor. If we go from one electrode to the other, the voltage increases or decreases depending on the sense of the voltage source in a linear fashion. So if you look at what happens without the intrinsic, this is if the intrinsic region were not present, we would have a standard PN junction or NP junction. Remember before that we had the P on the left side and the N on the right side. It was the mirror image. It was just this thing flipped over on its side of the electric field. It was negative here. The N is on the left, so the electric field is positive, and the slopes are indicated here. This is a little bit more to scale. It shows the heavily doped N region with a high slope and the lightly doped P region with a much shallower slope. And again, these are the intrinsic, these are the depletion regions here. So the quasi-neutral is over here for the N region, the quasi-neutral is over here for the P region. Okay, now if we want to find the total widths of the depletion regions, we use the formula which we've seen a number of times, and we find that the depletion region for the total is about just under a micron, and it's all on WP. So we have about a micron from the metallurgical junction right here to the start of the quasi-neutral region, and then we have 0.1 microns on the left side. That is if there were no intrinsic. Okay. Now, if we do have an intrinsic, let's go back to the pin. We have this 0.66 volts, which is the total barrier, which is dropped across 3 regions: the N region, the intrinsic, and the P regions. Okay, so we can express these drops across the N region and the P region by going back to this formula right here. If we're talking about W sub N, we use the ND part and we solve for VBI instead of W. That's why we have a square term here. And the same thing for the drop across the P region. This is just this equation which taken apart and basically used for each region separately. And we don't know the numbers yet. Well, let's see. Okay, so this equation comes from our standard equation, which is basically this equation right here. Okay, so let's take a look at this again. Okay, so if you take a look at these equations, this is for the PIN, not for the PN. So I don't know WN for the PIN. I know it for the PN, but I don't know it for the PIN. So that's one of the things we're going to find. So I can't use these equations directly because the depletion regions are going to be different for the PIN diode than they are for the PN junction diode. Okay. So to find the drop across the intrinsic, we consider, and we've mentioned this before, the two depletion regions basically as contacts of a parallel plate capacitor, where the distance between the electrodes is the intrinsic width. Okay, so we find that just substituting in V intrinsic, we find that it's equal to, well, what is it? It's equal to Q over C. And this is C right here, and Q is ND, QND. That is, oh, it got to be someplace. Right here. This is QND. Okay? That's the total charge. All right, let's see what we got here. Oh my. Must be, oh, there it is. Okay. So this is Q, and this is WP, obviously the depletion region in the pin diode on the P side, which I don't know. And of course, this is epsilon of silicon, which is 10 to the minus 12th. Okay. So that is this guy right here. We just basically say this is the drop across the intrinsic region, and it's right here. And this is the drop across. Oh, here it is. I knew it had to be someplace. This is the drop across the N region. This is the drop across the intrinsic region, and this is the drop across the P region. What do we know and what don't we know? Well, we don't know WN and we don't know WP. We know W intrinsic, that's 1.5 microns, but we know the sum is 0.66 volts. We have one more piece of information, and that is the areas under the charge concentration curves must be equal. Going back to, oh gosh, who is it? Oh, here it is. This area is equal to this area. And that is exactly what we have here. The areas, the height is this is the width, and that is equal to the height on the P region times the width of the P region. Here the height is higher, the width is smaller, the height is lower, the width is wider. So we can substitute in for WP, and we do that right here. We just basically, instead of WP squared, we substitute that in from here, and we have one equation with one unknown, which the one unknown must be something. It is W sub N, and here we put in everything that we know. The charge, 1.6 10 to the minus 19th, the doping density on the T side, Wn, which we don't know, we're going to solve, and here we do the same thing. All these numbers go in here. The intrinsic is 1.5 microns, which is 1.5 times 10 to the minus 4 centimeters. Epsilon of silicon is 10 to the minus 12th, so everything is looking good. And ND over NA is 10, so 10 squared is 100. That's here. So we have one equation with one unknown, and here it is. It is a quadratic equation, and here is this quadratic equation right here, and this is the form ax squared plus bx plus c. So we use the quadratic formula, and we solve, and we find that Wn is 0.04 microns, and Wp is about 10 times that, much, much smaller. Remember, Wn for the pin diode, not the pin diode, the PN diode, the PN junction was about a micron. Here it is dramatically smaller. And there is a decrease in the depletion region, and that accounts for the decrease in the electric field. And the electric field is just given by the charge density divided by epsilon multiplied by Wp. We put all that stuff in. That's Emax right here. And we find it's 1.5 times 10 to the 4th if it is for a PN diode. I'm jumping back and forth, and I apologize for that. I should have for the PN diode, the maximum electric field would be very straightforward, and it would be 1.5 times 10 to the fourth volts per centimeter. For the PN diode, we use the same thing, WP, but WP is much smaller, and we find that the Emax, instead of being 1.5 times 10 to the fourth, it is 6.7 times 10 to the third, a rather significant decrease at that. And the capacitance for a PN junction would be simply the epsilon divided by the distance, in this case, the sum of the depletion regions, which is about a micron, or 1 times 10 to the minus 4 centimeters. And for the PIN diode, we have a much wider, greater distance between the electrodes. The capacitance goes down, and that is very advantageous for high-frequency operation. Okay, we somehow struggled through this, and we should be very proud of ourselves. And now let's end with a musical, not a musical clip, a very, very nice, lovely clip. Okay, I hope you'll enjoy this. You may recall the movie, I believe it was called The Miracle Worker with Patty Duke. It was a fictional representation of Helen Keller. She was a woman who could neither see nor hear nor speak, and it told about her childhood. There's an Indian version of that, which later made in 2005. The movie is called Black, and it tells the story of a woman, start in her infancy, Michelle McNally, who can neither see nor hear nor speak. She only communicates through feeling, and yet she has a passion for learning. And she goes before a committee to be admitted into a university. We've seen people going before committees. Remember Alex in the movie Flashdance. It's not a very pleasant experience. So let's follow Michelle McNally as she goes before the committee in one of the very powerful and beautiful scenes from the 2005 movie Black. And I almost forgot to say, we'll see you next time.
Love was made for me and you. Oh yeah, love was made for me and you.
देखिए, एक लड़की जो देख नहीं सकती, सुन नहीं सकती, फिर भी just look at her, it's wonderful.
That's Michelle McNally. वही लड़की जिसके बारे में मैंने आपसे बात की थी.
That's impossible, Mrs. I.
Impossible is a word that I have never taught her, Mr. Fernandez.
ऐसे बच्चों के लिए स्पेशल स्कूल्स हैं, जहां उन्हें बहुत कुछ सिखाया जाता है.
टोकरी बनाना, चटाई बुनना.
क्या आपने कभी सुना है मिसेस सहाय कि ऐसे स्टूडेंट को आम कॉलेज में एडमिशन मिला हो?
नहीं, पर सुनना चाहता हूं.
पर क्लासरूम के लेक्चर वो कैसे समझेगी?
मैं बैठूंगा क्लासरूम में, वो उंगलियों से पढ़ेगी, मैं सिखाऊंगा उसे every word, every letter. Michelle, meet your principal. Yes, I've told him you want admission in arts, not science.
सहाय, ये फैसला मेरे हाथ में नहीं है. मुझे ट्रस्टीज को समझाना होगा.
इंसान को अच्छा काम करने का मौका बार बार नहीं मिलता, मिस्टर फर्नांडिस. I hope that you will not lose this opportunity. Yes.
Mr. Sahib, आप जानते हैं कि मिशेल जैसे बच्चे आम स्टूडेंट्स के साथ यूनिवर्सिटी में नहीं जाते, बट बिकॉज ऑफ योर फेथ इन मिशेल एंड बिकॉज वी बिलीव यूर अ गुड टीचर, हम मिशेल का इंटरव्यू लेंगे।
थैंक यू।
पर आज आप मिशेल की आवाज नहीं बन सकते। हमने एक स्पेशल टीचर को इनवाइट किया है जो मिशेल और आप दोनों को नहीं जानती। शी विल इंटरप्रेट। there she is. Welcome, Miss Nair. Meet Mrs. Sahai.
Hello, Miss Nair.
The interview. We're ready, sir.
Why does she want to study?
Why do you want to study? I want to study and learn so that I may live with dignity, with independence, and to be alive.
How many oceans are there in the world?
कितने महासागर हैं इस दुनिया में? मेरे लिए पानी की हर एक बूंद महासागर सी है।
She's not answering my question. दुनिया में महासागर कितने हैं?
उन्हें इस सवाल का सीधा जवाब चाहिए।
अगर वो हिंदुस्तान में है
If
तो
you
अमेरिका
are in
उसके किस
India,
ओर होगा?
Which side is America? The world is round, so America can be on any side.
What does knowledge
What
mean
does
to her?
knowledge mean to you? Knowledge is everything. Knowledge is spirit, wisdom, courage, light, sound. Knowledge is my Bible, God. Knowledge is my teacher.
Bravo! Excellent!
Congratulations, Mrs. Sahai. Your student is now a part of our university.